Okay, so let us begin once again with a quick recap. Okay, so what we did mostly was to look at WC comma WR regular LDPC codes, and we looked at Gallagher A hard decision decoding algorithm. Okay, so essentially this thing is a iterative message passing decoder. It operates on the Tanner graph, right. So the way we described it was there are two stages in the iteration. The first stage consists of messages being passed from the bit node to the check node, and the other stage consists of messages being passed in the opposite direction. Okay, and what are these messages? These messages are estimates of the, so these messages flow on edges, and a particular message that is flowing on an edge is basically an estimate of the bit node that the edge is connected to, always, irrespective of the direction in which the message is flowing, it is always an estimate of the bit node that it is connected to. Okay, and there are ways of doing it. For the first iteration there is some message that you send, and then in subsequent iterations you send another message. And we also saw this idea of density evolution, which is very crucial, which gives you a nice handle on what is actually happening. Okay, what is the idea behind density evolution? Okay, so tracking the probability that a particular message is going to be in error, right, that is the main idea. How do you track that? So you have to take a lot of care in doing that. The first assumption that is crucial in density evolution is that the all 0 code word was transmitted. Okay, so the all 0 code word being transmitted is a crucial assumption, and that can be justified by some means. And once you make that assumption, it is easy to track the probability that a particular message is an error. And essentially what you will have is, you will have a formula like this, right. So P L in the nth iteration, the probability of error in the nth iteration will be some function which is parameterized by WR and WC of P L minus 1, and then the P, which is the BSC transition probability. Is that okay? So this is a crucial method of analyzing, the crucial step in the analysis of LDPC codes. Okay, so there are ways of justifying this. If you want this formula to hold for L iterations, what should happen? Some condition, yeah, there should be no cycles of length 2L or lower. Okay, so the girth should be 2L. Okay, only then this formula will hold, and we kind of do not take that too seriously, and we say let it not hold, but I will still do it. And then we saw some simulation plots where that made sense. Okay, so that also made sense, and this formula is also useful because when n becomes really large, probability that there is a cycle in depth 2L goes to 0. Okay, in every neighborhood it goes to 0. So it becomes a reasonably good formula for large block length. Okay, and we saw that also in the simulation results. As block length increased, the prediction given by this formula was seen to hold more and more, right. So you saw that the curve was shifting closer and closer to the threshold line as n became larger. Okay, so another crucial property for this iteration is the threshold property. What is the threshold property? Okay, so you can show that there is a P star such that P infinity is 0, right, the maximum P. Okay, so let me write this a little bit more clearly. Okay, so okay, so threshold is the maximum P such that P infinity is equal to 0, right, in this iteration. Okay, so you keep on increasing P from 0 onwards. Of course, if P is 0, P infinity is also 0. As you keep increasing P infinity will continue to be 0 for some time. Okay, after that it will shoot up to a non-zero value. Okay, so the maximum possible value for which this equal to 0 happens, P infinity equal to 0 happens is called the threshold. Okay. Remember once again, technically you cannot say maximum because such a maximum will not exist in that set, it will be supremum or something, but maximum is good enough for us. Okay, we will stick to that. Okay. So any questions or comments on this? Okay, all right. Okay, so then if you actually look at, so there are some thresholds that you can look at. I think I didn't do it last class, but I'll briefly tell you. So if you now make like a table of WR, WC and P star, say for a particular rate, so let us say rate equals half. Okay, what are the various WR, WC possible? This is P star for the Gallagher A. Okay, Gallagher A decoder or Gala decoder, sounds like a better terminology. Okay, so if one thing you can do is, so I should say WC, WR, right? For some reason I always like saying WR, WC, I do not know why. Okay, so 3,6 is one choice which gives you a design rate of half, and that threshold happens to be 0.039 if you want to be very exact. Okay, another possibility is 4,8, right? 4,8 also gives you a design rate of half. Okay, and this would give you in fact a threshold of 0.047. Okay, and then 5,10 gives you a threshold of 0.027, and then progressively it only worsens. Okay, you can do this if you like. If you take 6,12, it will be even lower. Okay, so those are things you can look at. Okay, so if you stick to regular codes based on threshold, which is the best degree distribution? 4,8 is the best, seems like the best degree distribution. Okay, but really there is not too much choice here. I mean, if you stick to regular codes, it seems like there is not too many choices, right? So just one or two you can take, and then quickly you settle on the right answer. Okay, so this basically prompts the move towards irregular codes where you allow multiple degrees, multiple bit node degrees, multiple check node degrees, or in terms of the parity check matrix, multiple column weights, multiple row weights, not just a single one, and then see what happens to the threshold. Okay, so if is there a threshold, etc., all that you can study, and then maybe there will be better thresholds than this. So remember, if you want to know capacity, it turns out for rate half, capacity achieving probability is basically capacity will come at P equals 0.11. Okay, so what this means is if your channel transition probability is smaller than 0.11, you can have rate half for large enough block length. That is what it means. Okay, so for a comparison, if you compare these two guys, it's a bit far. Okay, there is a gap. Okay, P equals 0.11 is capacity for rate half. The best we are getting with regular codes is 0.047. Yes, is there a question? Yeah.
The code rate.
Yeah. So okay. So the question is, design rate is half. What about the actual code rate? If you compute the rank, it might become 1/10 or something. It won't become. Okay. So you can show some results where if you pick your matrix at random with very high probability, you will have rate close to half. It's difficult to get linear dependence in sparse matrices. Okay. Okay, so now we moved on to irregular codes, and I defined something called the degree distribution polynomials. Did I define the degree distribution polynomials? Okay, so with the node perspective, we defined it with node perspective. Node perspective degree distributions. Okay, basically capital L sub I is the fraction of nodes with degree, fraction of bit nodes or left nodes with degree equal to I. Same is the case with Ri. What is Ri? Fraction of right nodes with degree equal to maybe Rj, okay, just to say, use some other dummy variable. Okay, and if you do this based on the design rate, there are constraints. Okay, the first constraint is that summation Li should be equal to 1, similarly summation rj should be equal to 1, right. So, these are all fractions, clearly they should all add up to 1 fraction of nodes, okay. And then you can compute the design rate. The design rate will turn out to be something like this: r equals 1 minus summation I Li divided by summation j r j, okay. So, you can also define some polynomials if you like, summation Li x power I, r of x is summation r j x power j, okay. And then in terms of those polynomials, this will be L prime 1 divided by r prime 1, okay. So, these are just convenient forms for expression, okay. So, one example I gave for r half, I think you computed this for design rate half. We had one example, L of x being equal to x squared by 2 plus x power 4 by 4 plus x power 7 by 4, and then r of x is equal to x power 7 by 2 plus x power 8 by 2, okay. So, one thing you can try, for instance, is to say I will allow degree 2, degree 4 and degree 7 for the left nodes, okay. Let me not fix the fractions now, I will simply say I will allow degree 2, degree 4 and degree 7 for the left nodes. So, what does that mean? It means L2 is not 0, L4 is not 0, L7 is not 0, okay, and L2 plus L4 plus L7 is 1, okay. All these cases are between 0 and 1, and for the right hand node I will allow only degree 7 and degree 8, okay. Everything else I will make 0, okay. Suppose I add those two constraints, okay, how many possible degree distributions will you have for design rate half, okay. So, that is those kind of questions you can ask. These are simple questions, there will be some answers for that also, okay. So, first of all you have one equation for else, right, and one equation for r saying summation Li is 1, summation Ri is 1, and then there will be one more equation fixing the design rate to be half. What kind of equation will that be? It will also be a linear equation, okay. So, you have 3 linear equations, and how many variables do you have? 5 variables, and they are forced to be between 0 and 1. So, you have some inequality constraints also, but in general you can expect an infinite number of solutions, okay. There will be a huge number of solutions, okay. Is that fine? So, in fact you do not have to put a constraint on the sum of Li and all that. So, you can do some adjustments with that, and if you want you can exactly solve these problems, but it is not so critical today. As long as there are linear constraints, nobody is scared about linear constraints, okay. So, it is very easy to program, so you can do that. So, the final point I want to make is, even if you restrict your degrees to be a few more than constant, okay, for a particular design rate you will have several degree distributions, okay. So, this was just one such degree distribution. Several such degree distributions are possible for a given design rate. Given design rate R, okay. So, this increases your pool of candidate codes and candidate ensembles, so to speak. It is not codes, right. So, when I say codes, always remember when I say LDPC codes, it is just an ensemble. When I fix the degree distribution, the code never gets fixed, okay. So, you have to pick a random member from the random matrix from the ensemble, okay. So, you have such a huge set, and hopefully if you come up with a density evolution formula for irregular codes, okay, if I have formula only for regular codes, if you do so for irregular codes, you can optimize over all these degree distributions for a particular design rate to get the best possible threshold, okay. So, that is the basic idea behind moving towards irregular codes, right. In the regular codes we saw that there is a gap between the capacity and the threshold that it is achieving. So, maybe you can do a little bit better there, okay. So, that is the basic idea behind moving towards irregular codes, okay. And you can see that there is a huge number of degree distributions for a given design rate, okay, and even if you fix the number of allowed degrees, there is a huge number. Okay, so if you vary that also, you get a even bigger number of possibilities.
Searching like the whole space for the best one are very huge.
Yeah, so okay, so the question is how complex will this search be? Yeah, it will be very complex. Okay, so I'm not saying it will be very easy, but it's doable. Okay, today computers are powerful. There are very powerful algorithms like whatever differential evolution is a very common candidate that's used. All these genetic type algorithms for optimization. So you can use all these, throw some very heavy machinery at it. Eventually, it will work. Okay, so yeah, so that's the idea. But the idea is, the other thing is, you don't have to do this at some 1 gigabit per second or something, right? So this is some initial design that you're doing once and you freeze it. That's all. So you do it as you can take like 6 months to do it. As long as it works at the end, you're done. So you don't have to do it online or anything. Okay, so let's see how to go about doing this. So of course, coming up with construction for irregular degree distribution also is a little bit tricky, right? So for regular we had some constructions, but you can always define a socket construction. Okay, so we will always think of a socket ensemble for irregular codes. So how do you do the socket ensemble? Okay, so you have L1n nodes of degree what of degree 1. So I am not going to put degree 1. Okay, so I will just start with degree 2. Okay, L2n of degree 2 and then L3n of degree 3 and so on, right. Finally maybe some L I do not know, what do you want to call this guy, the maximum, maybe I will put capital I here. Okay, so L capital I n bit nodes. So all these guys have degree 2. Okay, all these nodes have degree 3, etc. Okay, so the first set L2n has degree 2, the next set L3n has degree 3, so on. So what can I do? I can put 2 sockets in each of these nodes. Okay, then I would put 3 sockets in each of these nodes. So until I will put how many sockets here? I sockets in each of these nodes. Okay. Now the same thing I can do for the check nodes also. There is going to be R2 what? R2 m, right? M is the number of check nodes. It's not n. So m is the total number of check nodes. Okay, so likewise all the way down to R capital J m, and I would put 2 sockets here, and I would put J sockets here. Okay, right. So now you have to count the total number of edges. What is the total number of edges? Okay, so there are 2 ways of doing it. It is going to be summation I Li times what? Times n, is that correct or not? Right, that is from this side, and this will be the same as summation j r j times m. Okay, so this is the total number of edges. Maybe I call it some n e. Okay, what do? I pick pi to be a permutation of n-e objects, okay, and then place the edges according to this random permutation. Okay, so you number the sockets from 1 to n-e on the left side, you number the sockets from the same 1 to same n-e on the right side. There will be exactly n-e sockets on both sides, right. Pi will be a permutation from 1 n-e to 1 n-e. Okay, so for each permutation you will get a code. Okay, of course the multiple edge problem still remains. So let us say we throw away all the multiple edges, for instance, and then you get code from the ensemble. Okay, So, technically for any irregular degree distribution also you can do a socket construction, there is no problem. Okay. So, construction is okay, specification seems okay, design rate seems okay. The only next step is to look at decoding. Okay. So, once we are sure that the decoding that we had, the Gallagher A decoding for instance, also extends to the irregular case. Okay. So, that is a good first step, and then we want to extend density evolution to the irregular case. Once all of those is done, then you can go ahead and work on this complicated optimization or search for the best possible degree distribution for a particular design rate. Okay. So, that is the next two steps that we will tie and do. Okay. So, what about Gallagher A decoding? Okay. So, before this, if you want me to mention what will you do about encoding? What about encoding of irregular codes? Yeah, so that is it. So, once you have the parity check matrix, encoding is at least in principle trivial. Okay. So, you do a Gaussian elimination, convert it into systematic form and then do the encoding, right. So, that is going to be a little bit more complex. If you want to do efficient encoding, there are ways of doing that also. So, all those things will extend without any problem. The critical thing is the decoding. Okay. So, let us see how the decoding extends. Okay. Decoding is also actually quite simple. Remember, how did we describe Gallagher A finally on the Tanner graph? Each iteration had two steps. In the first step, the messages were passed from bit nodes to check nodes. Okay. In the regular codes, each bit node was connected to the same number of check nodes. Okay. You had WR on each side, but what will happen in the irregular case? They will be different depending on how many there are. You simply pass that many messages, that all. Okay. The same principle holds. You send messages on the edges. Message sent is a estimate of the bit node that it is connected to, except that in the irregular case, every bit node will not do the exact same thing, as in it will not have the same number of neighbors, that is all. The principle is the same, it will pass messages according to the same algorithm only, but bit node of degree 2 will send out only 2 messages, while a bit node of degree 10 will send out 10 different messages, that is all. So, other than that, I can very easily write down the rules for the iteration. Okay. So, I am going to say Gallagher A decoding same as regular with some codes. You have to just understand that there is one minor change, as in the degree is different. Okay. So, what is the, so how does this, how will this look? So, you have a bit node which is connected to, let us say, I check nodes. Okay. So, let us say degree here is I. Okay. So, what would have happened in the L minus 1th iteration? You would have got, I think if I remember right, I called it U L minus 1, is that correct? U2 maybe, right? Okay. So, you will go all the way down to U I L minus 1. Okay. So, maybe I should write this again. Okay. So, the message that was received in the previous iteration is like this. Okay. And the message that is passed from on the first edge in this iteration is V1, let us say L. Okay. How do you decide V1 L? If all the U's agree equal to B, then V1 L equal to B. Okay. So, let us say the channel received information is R, else V1 L equals R. Okay. So, the rule remains exactly the same, except that there might be some bits which are connected to only 2 nodes, 2 check nodes, and there might be some bits which are connected to more than 2. Okay. So, depending on what they are connected to, you simply change the degree there, and you have this exact same rule which you can repeat. Okay. There is no complication as far as the iterative message passing decoder is concerned. Okay. It works on even an irregular graph exactly the same way without any problems. Okay. So, what happens on the check node side? Okay. So, the check node might have degree j, which means that if it receives V2L all the way down to Vjl in this iteration, it should pass back U1L, and what will U1L be? The XOR of all these guys. That is it. Okay. So, essentially the decoding extends very trivially, there is no problem in the decoding. Okay. All right. So, you can run this decoder, okay, and if you want to measure performance for the decoder, you have to have some analysis. Analysis is good, but if suppose we cannot analyze, what would be a very brute force way of analyzing the decoder? You have to do simulation, right? But then if you want to simulate down to 10 power minus 3 frame error rate, you have to simulate 100,000 blocks. Okay. So, one way of optimizing the degree distribution is doing what? You pick a particular degree distribution. How do you measure the performance of the degree distribution? You simulate and recreate the create the BER versus EB over N naught picture. Okay. It will cross say 10 power minus 3 at a certain point, you find that point, and then you find one more degree distribution, see how it behaves. Okay. So, that would be one way of measuring performance. Okay. But given that we have a huge number of degree distributions, some procedure like this will not even converge in finite time, even though you have like 6-7 months in your hand, you may not be able to do anything with that also. Okay. So, you really desperately need some way of extending the threshold analysis. Okay. Even if it is approximate, even if there are some hand wavings done here and there, even if it is not very exact, if you have some number which can be easily computed given the degree distribution which measures the threshold, so to speak, then you can optimize the degree distribution for that number. Okay. So, in fact, it turns out the threshold computation is also hard. We will not have a closed form expression for threshold. Even in the regular case, we did not have a closed form expression, right. Actually, for this algorithm, maybe you can get some approximations, but it is very hard to get a closed form expression, I think. So, in the general case, you may not be able to. Okay. So, for the irregular codes also, you may not get a closed form expression, okay, but at least numerically you should be able to evaluate the threshold, and that might be way better than doing 100,000 blocks of simulations and actually implementing the decoder, and you do not know how many iterations to do. Remember, the block length n is going to be very large, right, n is going to be 100,000 or something, and then you have to do so many iterations, some hundreds of iterations you have to do. So, it takes a long time to finish, that takes a long time to finish. Okay. Till computers reach that stage, you still need some analysis of how this is going to work. Okay. So, let us see how to extend the density evolution. The way I will describe it, I will do a kind of a hand waving justification for some things. Okay. So, there is a slightly more rigorous justification possible, but at the end of the day it is an approximate analysis. Okay. So, I will try and mention the main steps and give you some guidelines on how to understand it, but I will derive it with a very simple kind of hand waving kind of idea. Okay. So, that is how well I will derive it. Okay. Right. So, the basic idea is we want to repeat the same analysis that we had before, right. So, we want to do density evolution. Okay. How did density evolution work in the previous case? We had two different quantities that we tracked across iterations, right. There was this PL and then the QL. Okay. PL was the probability that the message from bit to check was an error, and QL was the probability that the message from check to bit nodes was an error. Okay. So, I will give you a simple way of getting an approximate expression for these things in the irregular case. Okay. So, there will be some holes in the way I describe it. To rigorously properly justify it, you need some, well, one more course maybe. Okay, so maybe it's not possible in this course. I won't do too much of that. Okay, then later on I'll mention all the caveats and what else is needed to make it a little bit more rigorous. Okay, so okay, so that's what we are going to do. Okay, so but before that, the all zero code word assumption can be justified in the same manner as before. Okay, so we will actually we did not really justify the all zero code word even before, but it can be justified. Okay, so I'm not going into that detail, but you assume the all zero code word and that's no problem. That will be justified for the same reason that it works for regular codes. So it's no problem, that extends without any approximation. Okay, so like before, I want to have PL to be probability that VL is equal to 1, and likewise I also want to have QL to be probability that UL is equal to 1. Okay. So now comes a crucial point in defining VL and UL. Okay. So in the regular case, I really had no problem in defining VL and UL to be, I mean not defining, and assuming that VL and UL were IID, right. That was a crucial assumption, right. If you remember in the analysis, we had to assume that VL, so the message on a set of edges. Okay. So one of the crucial assumptions was in the Lth iteration, VL is what? This is the random variable that denotes the message from bit nodes to check nodes. The assumption I will make is, if you look at all the edges, right, the message that goes on each edge is distributed IID according to VL. Okay, that is the assumption that I made, right. That is what I mean when I say message from bit nodes to check nodes is distributed according to VL IID. Okay. Same thing is true for UL. I will be assuming that messages from check nodes to bit nodes are distributed IID according to UL. Okay. In a regular graph, this can be justified very easily, because if you look at the message on a particular edge, it depends on so many prior messages, and for that we had a computation graph, right. So there was a graph that we drew, the kind of like a tree, and the tree looks identical for each edge in the regular ensemble as long as there are no repetitions. Okay. It looks identical and we can justify that very easily. What will happen in an irregular case? Yeah, it is not going to be the same, right. So there is no way I can say I can analyze any one particular graph. Okay. Even if there are cycles or no cycles, just because the degrees are different, for different edges will clearly have different computation graphs. Clearly the message will be computed in a totally different way for one edge and the other depending on the degree. Okay. So I have no business in saying the message from bit nodes to check nodes is distributed according to VL IID. Okay. So that will not work at all. Okay. So the first trick you have to use here is, this is message from bit nodes to check nodes, you have to average over all possible graphs. Okay, so this trick is very important. So you can't analyze a single graph anymore. Okay, so you are given one regular code realization, we were able to do density evolution for that. In the irregular case, to be able to do a decent density evolution, when I say decent, I mean you do not want to track like a million messages. Of course, if you track a million messages, you can do it, but we can't do that. So to have some control over the process, you have to assume that all the messages have an IID distribution. The only way you can do that is when you average it over all graphs in the ensemble and not just any single graph. Okay, so that is the first kind of approximation that will enter the analysis. Okay, I will no longer look at one graph, I will look at all the graphs and average over them. Okay, so it turns out you can justify this IID nature when you average over all the graphs. Okay, so I am not going to go into great detail there. In fact, you can justify it only as n tends to infinity. Okay, in the asymptotic situation, it is justified. Okay, so let's leave it right there, and then again for UL also the same thing holds. Okay, once again you have to average over all graphs in the ensemble. Okay, only then every edge will be equally likely to have come from an average kind of neighborhood which looks the same. Okay, that is the idea. Okay, so I do not want to go into great detail here, but we will just remember that the messages that we will be tracking are not the messages on a particular graph. You are not fixing a graph and doing decoding, and you are not tracking messages there. What is the message that is being tracked? You will be looking at all the graphs together. Okay, so all 0 code word is being received over the BSC. That same received word is being decoded by all graphs from the ensemble. How many graphs are there? A huge number of graphs. Okay, and all is very large. Okay, so a huge number of graphs. All of them are being decoded. Decoding is run simultaneously. Then what message will I track? An average, an edge that I pick randomly from all of those things. Okay, so that message I will track. And that I can say will be IID. Okay, it seems to make sense. When you look at so many huge things, maybe it's IID. It's not too difficult to justify it. Okay, so there are rigorous ways of justifying it, but intuitively that's what's happening. Okay, that's the picture you should have in mind. I don't have one graph. I'm not tracking the message on one graph. I will first pick a particular edge that I can specify in the socket ensemble, right? So number from edge out of this guy, maybe you can specify that, and then that one you have to now look at every single code. So its neighborhood, in each code the neighborhood will be different. You kind of average over all of those things. Okay, that's the idea. So I don't know, did I do anything wrong? Oh man, it made a nasty noise. Okay, all right, so we're back. So it's a bit of a, like I said, it's a bit of a fishy idea. You have to justify it very carefully. Okay, and we will not see the justification in this class. I'll urge you to look at the book by Urbanke and Richardson, Modern Coding Theory. They have a very good justification of this, and there's lots of detail in that book. Okay, so if you're interested, you can take a look at it, but we'll proceed with like I said, my own pseudo interpretation of that, and I'll give you a simple derivation. Okay. So remember, we are interested in tracking the density, tracking the probability of UL and VL being in error through these two steps. There are two steps in the iteration. One step is the processing at the bit nodes, and the other step is the processing at the check nodes. Okay, so we'll start with the processing at the check nodes. Suppose I have a check node with degree j. Okay, so remember once again. Okay, so so for some reason it is not. Oh. Okay. I think it's not, maybe it's not the standard one, no? Pen. Okay, there you go. Okay, so I want to pick a random edge. Okay, what do I mean by random edge? Okay, so when I say random edge, the edge can be from any one of the codes. Okay, so there is a huge number of codes with the same degree distribution, and I want to pick a random edge from this code. Okay, so you pick a random edge and then ask the question, okay, what is its right degree and what is its left degree. Okay, so you have to ask that question, because only then you can do the evaluation, right. So when I want to do the evaluation of when I want to find QL or PL, the probability that the messages are in error, the degree of the check node and the degree of the bit node plays an important role. But then I can't analyze the probability of error on any particular edge. I have to pick the edge at random. Okay, so when I keep doing this at random edge, when I pick a random edge, you have a probability that this random edge is connected to a certain degree check node, and a probability that this random edge is connected to a certain degree bit node. Okay, so let's try to compute that. Okay, so if you pick a random edge, what is the probability that right degree equals right degree of edge? Remember, what do I mean by right degree of edge? The degree of the check node that it's connected to. Okay. So, what is the probability that this equals j? Okay, how will you answer this question? Okay, so this will basically be, okay, let me remove the question mark. This will be the fraction of edges arising from degree j check nodes, right. That is the idea. So, in a graph you have so many, several check nodes of different degrees, okay, and so there will be several edges which originate from different degree check nodes. Okay. So, when I pick a random edge in a particular graph, even in a particular graph, a particular edge is likely to be connected to a check node of degree j with a certain probability, and the probability will be equal to the fraction of edges that come out of degree j check nodes. Okay. And this fraction can be very easily computed. What will be this fraction? J times Rj times m divided by summation j Rj m. Okay. So, m will cancel. So, you simply get j Rj by summation j Rj. Okay. So, since this quantity figures with such importance in our analysis, we will call it rho j. Okay. So, give it a new name. This is the probability that the right degree of a randomly chosen edge is going to be equal to a particular j, that is rho j. Okay. So, this is also called the edge perspective degree distribution. Okay. So, capital R is the node perspective right degree distribution, rho is the edge perspective right degree distribution. Okay. So, it basically says what is the probability that a randomly chosen edge even in a particular graph will be connected to a degree j check node. Okay. So, the same question you can ask for the left degree, probability that left degree of a randomly chosen edge equals I. Okay, I am using I and j, these are just dummy guys. This will be also again fraction of edges arising from degree I bit nodes. Okay. So, we will call this lambda I. Okay, this is just notation. Okay. And just like before, you can quickly see that this will be the formula, right. I Li divided by summation I Li. Okay. So, these two fractions will play an important role in the analysis. Okay. So, that is fine, let us accept those fractions as reality. So, now when I do that, let us see how I can go about doing this analysis without too much pain. So, what I am going to do is, I am once again going to look at a check node of degree j. Okay, and then look at the messages that are coming in. It will have j edges connected to it. Okay, so this will be j minus 1, and this will be the message that I am interested in. Okay, what is the probability of error in this message? Okay, so I would have received some messages from these j minus 1 guys, and I will be sending out a message in this direction. I want to look at what is the probability that the error in this message. Okay. So, remember what is the probability that all these incoming messages are in error? That is going to be IID according to VL, right. Probability of error here is some PL, okay, and it is IID, right. That is given to me. I have to now compute the probability of error in that message, and for that I know the formula already. Okay. So, that formula is very simple. This will be 1 minus 2 PL power j minus 1 divided by 2. Okay. So, that is the probability that I have an odd number of errors in this j minus 1. Okay. That I can do for a particular check node of a particular degree j. Now, this edge that I chose has a probability rho j that is connected to a check node of degree j. okay, and that j can vary. Okay. So, if I want to average over all possible graphs and all possible edges and all that, when I want to do that, then QL will become the average of this guy averaged over rho j. Okay. So, that is the idea, rho j times 1 minus 2 PL power j minus 1 divided by 2. Okay. At this point I have to ask you a question, how many of you think that this is a very rigorous analysis? Okay. Well, it is not very rigorous. Okay. So, I am just doing it just like that. Okay. I am giving you an intuitive justification. Okay. So, this is just an intuitive justification, it is not rigorous. Please see the book if you want a more rigorous justification. If you are already convinced that this is rigorous, then well and good. Okay. So, you can be very happy, there is no problem with that also. Okay. So, that is the formula. Okay. So, j will go from 1 to capital J if you like. Okay. So, that is the idea behind this analysis. Okay. So, this is for QL. Okay. So, now I have QL, I will repeat something very similar for the bit node also. Okay. So, what do I do for the bit node? My bit node, suppose it has degree, bit nodes maybe has degree, sorry.
Possible edges that I might pick.
Yeah.
But what about all possible graphs?
Well, all those things are, I mean, I do not know, I mean, what is the question again? I did not understand.
Here we picked a random edge in one graph.
In one graph,
Yeah.
okay.
So, and we said that okay, on an average this could have had this much degree.
Yeah, okay, okay. So, you are asking why did I need the averaging over all the graphs? That I need for this kind of IID assumption. I am saying probability of error is PL, right, for all of them I am taking to be the same.
Here we have, in this case I have picked a pixel graph. Now,
Yes.
in this particular, this thing, how we are assuming that if
This
we take
graph.
an average of this over all possible graphs, then we can take it. In this particular case, when we did this
Okay.
analysis,
Okay, so I do not know how to exactly answer your question, but there is, like I said, this is only an intuitive justification, it is not very rigorously valid. You have to do something a little bit more careful. Okay. So, you have to define an ensemble of neighborhoods of an edge and put probabilities on each of those and then average over that, and that also turns out to be the same rho j. Okay. So, that is why it actually works. Okay. So, but instead of doing all that work, I can give this hand waving justification, say that it is justified based on all these things. Okay. So, that is the hand waving part in this. Okay. It is not rigorously justified. Okay. So, you have a bit node, let us say it is of degree I. Okay, then it will have I minus 1 guys from whom there will be incoming messages, and there will be an outgoing message whose probability of error I want to compute. Okay. So, once again this guy probability of error will be is very well known to me. Okay. So, this is going to be 1 minus p times QL minus 1, no? I do not know, I think this is, yeah, I think QL minus 1 raised to the power I minus 1 plus p times 1 minus QL minus 1 raised to the power I minus 1. Okay. So, this is the formula that I know. Okay. And what will I do for PL? I will simply sum over I going from 1 to capital I, lambda I, which is the probability that my randomly chosen edge, so to speak, is connected to a degree I bit node, and then I do this same guy, just multiply by 1 minus p q l minus 1 raised to the power I minus 1 plus p 1 minus q l minus 1 raised to the power I minus 1. Okay. Is that fine? All right. So, I have a way of going from QL minus 1 to PL, and then I also have a way of going from PL to QL. Okay. Now, I can repeat this process, and in general I will finally get a density evolution formula for PL, which will be a function and the parameterization will be, in simple terms you can write it as lambda of x and rho of x. What is lambda of x and rho of x? Yeah, there will be some polynomials involving the lambdas, so I will write that down. Okay, so where lambda of x is simply summation lambda I, it's common to write x power I minus 1 instead of x power I here for lambdas. Okay, so I will tell you why soon enough, but it is usually written like that. Rho of x is written as summation rho j, once again x power j minus 1. Okay, there is a very simple reason why they do j minus 1 instead of j. For node perspective it is common to do j, and then for edge perspective we do j minus 1. Okay, that is all. So, this is the density evolution formula, but remember this is not valid for a particular graph, it is valid when you average over all graphs. Okay. So, how good is this is an important question that we have to ask. Okay, we will answer that soon enough, but this is the idea. Okay. So, what is the summary of this lecture finally? So, even for irregular codes, okay, so you have same ideas extending. Okay, what are the same ideas? Decoding, message passing decoding definitely extends. More importantly, density evolution extends. Okay, it's average density evolution. Okay, and we did not provide a very rigorous justification for it, but like I said, it can be justified in a more rigorous way than what I gave you right now. Alright, so we will stop here for now, and in the next lecture we will move on and see something more about this density evolution.